Hello ladies and gentlemen, welcome to the course on strategy game programming in the winter term 2020 and consecutives. My name is Horst Eidenberger. This is a course in the bachelor programs of data science as well as for all other bachelor studies as a free course. Today we will go through the contents of the lecture mostly. I will only skim over the first part, which is an introduction to the workings of the lab course, what you have to provide, what requirements have to be met, when you have to submit, how you have to submit, and so on. Okay, as I said, there will be an online meeting on that topic. If you have any questions, get in touch with your lecturer, that is, post something to the forum in the e-learning course. The link to the e-learning course is given at the end of the slides, but also in the TU information systems. Okay, after the pre-lecture meeting, I will give you an introduction to the major algorithms used in strategic planning and also in strategic gaming. It's the same, essentially, it's just one application gaming of strategic planning. Then we will go through heuristics, so how you can optimize the fundamental algorithms, and eventually we'll go through a few links of assets that you can use and will have to use. So what's to come? It's about games with at least 2 players, where you can build strategies which are move-based and which have full information and new from 2020 on. Also might have just partial information, but we come to that. Essentially, you have to apply algorithms from the area of reinforcement learning, in particular Monte Carlo tree simulation. That includes simulating the outcome of games of certain strategy and optimizing that simulation with heuristics. Yeah, as I said, the fundamental thing is managing the dilemma of exploitation versus exploration. You will learn the term of upper confidence bounds, UCB, which is very important. We will also do plain depth search with the alpha-beta algorithm. And briefly, we will have a look at the Dijkstra, the graph search algorithm that is still state-of-the-art. What are the educational goals? After this lecture and after the lab, you should be able to implement and understand plain depth search, which is sometimes superior to more sophisticated reinforcement learning techniques. You also have to understand the Monte Carlo tree simulation, and that is what you have to implement. You have no choice if you go for full information, but you have to pick Monte Carlo tree simulation. You're not allowed to do depth search anymore. And you have the practical experience in Java of implementing such an algorithm. It might come in handy if you later work in the area of logistics where these algorithms are practically applied. Okay, there is only one lecture block. It is not online over Zoom. I decided to record it, so what you see here is not correct. The contents are not so much the pre-lecture meeting as rather the settings, the algorithms, and the heuristics. And I will also give you some background information and hints what can be done. At the most, we should take 3 hours. I think it will be rather like 2 and 2.5 to get through the information. Okay, there will be no exam in this course because it's mostly a free course except for data science. But there you can also choose it as alternative to others. But you will be graded on your performance in the lab course and of course on your participation in the forum. Should questions arise, feel free, if you know the answer, to answer your colleagues, to help them. That is always the best way of learning something, by giving others advice and therefore being forced to formulate your knowledge in words. Okay. The most important thing is there is a registration test in TU Wien. Normally this course is massively overbooked. That means something between 70 and 100 students, where normally I would take 20 and this year I take 30. Therefore, you have to pass the registration test and only the first N students will be admitted to the course. By 15th of October, I believe, you will already know if you're in the course or not. Results will be published in an anonymous form, of course, in the TU Wien forum. Okay, for the lab projects, you can go for one of two, either for the Kalaha game with full information, which is an African bean game from the Mancala series, or you can go for the Risk game, which is a strategic game, military game, which is also turn-based and but has partial information for two reasons. Sometimes you don't know the situation, depending on the type of game you play, of your opponent or opponents, and certainly you don't know the outcome of battles because they are based on chance. Okay. What you have to do is you have to make use of the Java environments provided for these two games. You have to implement your own game engine. There are how-to documents linked in the e-learning forum that explain how this is done. Essentially, all you have to do is to implement clever heuristics, because the fundamental Monte Carlo tree search is also already there. You have to finish your project until mid-January. The exact deadline for the intermediate hand-in, which is also compulsory, and the final hand-in are both given on the TU forum front page. Submission is simply packing everything into a zip file and sending it to me, to my email address, and I will acknowledge every single submission. You can do repeated submissions, of course, only before the deadline. And then once I have all the submissions after the deadline, I will set up a tournament where each engine plays against every other, and eventually I will post the results in the forum, and after that I will grade your projects. Okay. Furthermore, there is an update that from the summer term 2022 on, there's a third game now. You can play a real-time game, which is based on the classic Empire game with armies fighting each other and the cities producing units. That is open only for expert Java programmers with experience, because it's a new environment. There might be bugs in it, and we have to sort them out during the term, and for that you need a certain level of expertise. That is the first update. The second update that I have is that since the course is very popular, I'm not just offering it now in the winter term, but also from 2022 on in the summer term. And then, of course, project time isn't until mid-June, but it's still the same TU e-learning course, and there you find the exact dates. The procedure of the submission of the hand-in stays exactly the same as it was in the past. Okay, assessment is mostly based on the quality of your algorithm, on the creativity of the approach, of the quality of the code, a little bit also on the performance in the tournament, but usually there are projects who don't perform because they're very risky and implement something really novel. And these are then, of course, still graded as very good. As I said, this is mostly a free course, so the grading is not as tough as it would be for a mandatory course. Usually they're only 1s and 2s if you submit something interesting. Normally the intrinsic motivation of the students is very high, so it has never been a problem so far. Try to be as active as possible. There's only one thing I don't like. This course is mostly easygoing. Only exception is when it comes to plagiarism. Every submission is checked against all other submissions of this year and of all other submissions so far in the course since 2014. This is done automatically. Please don't use code that was used by somebody else before. If you do that, there is no reset, there is no negotiating, you get a negative mark, and that was it. I've absolutely no understanding for that. If you are unsure what plagiarism is, please go to one of the linked documents of the faculty and of TU Wien, our code of conduct, plus the TU Wien's guideline on plagiarism. Don't do that. It is relatively simple to implement your own game engine. You can really go almost immediately to the creative part of trying different heuristics and developing them. And that is what you should do. Okay. So, in summary, you have to find a partner and form a group. Groups always consist of 2 students. It's never 1 student alone. It's never 3 students. Then you pick a game type. It might be Kalaha, it's the simplest one. It might be Risk if you're interested in working with partial information and elements of chance. Or you might pick Empire, which is a real-time game, but this is only for experienced Java programmers because it's a new environment. There might be bugs in the code which we have to sort out during the term, and for that you need a certain level of expertise. Then you implement a cool game artificial intelligence agent for your game. You submit it on time. If possible, you beat the others in the tournament. And very important, you do not cheat. Implement your own creative ideas, put them into code, and then it's a fine project. Well, then we come to the first section of the lecture, which is on the fundamental algorithms. This is the most important educational goal. You should know the depth search, alpha, beta, and you should also know the Monte Carlo tree simulation, which is the paramount algorithm today in games such as Go and also in planning problems like, for example, solving calendar problems. Shift computation. Well, a very brief history of game machines. The image shows the so-called Turk, which was a machine that looked very mechanical in the 18th century. It was developed by a German named Kempelen, and it only looked mechanical. It was not a mechanical chess playing machine. It was rather a fake where a very short man would sit inside the machine and would actually do the playing. But Kempelen exploited the spirit of the time, which was Enlightenment, and the idea was that with mechanics and with modern technology of that age, it would be possible to solve all problems, and that was what the Turk was based on, and it was highly popular. It also played here in Vienna, I think, against members of the Wiener Hof. Also, and one, of course, games, the gentleman who actually played was a very good game. Why was it called the Turk? Because Mr. Kempelen would be wearing a dress such as a noble from the Turkish Hochpfad. Okay, well, that was about the first occurrence of the idea of a machine that can do intelligent strategic gaming. Then there was a big gap until in the 1950s. First scholars started to develop ideas of what algorithms could look like. One of them was Claude Shannon, who is famous for his works on information theory, the entropy formula, and the Nyquist-Shannon law, for example. He was a scientist at the Bell Laboratories of AT&T, and he also did studies on playing chess. His studies were of a theoretical nature, so he would not implement anything. The first chess programs on computers would emerge in the 1970s. At that time, very weak. I remember myself playing against early machines in the mid-end 1980s, and those were usually easy to beat on the normal computer hardware, of course, not on specialized mainframe hardware. In 1997, Deep Blue was developed, or Deep Blue was shown to the public, developed by IBM. That was a big number crunching machine based on a mainframe architecture and with state-of-the-art depth search and all sorts of heuristics and optimizations. It managed to beat for the first time the world champion Garry Kasparov in long games. I think it was multi-hour games and not short games. That was, of course, a breakthrough. Until then, master players with ELO rankings of 2,500, 2,600 or above would not be beatable for machines. So it was a huge breakthrough, but it was not based on intelligence, but on number crunching. Only in 2009, the first Go algorithm, Go is a way more complex game. What complexity means, we will learn in a minute. MoGo would reach Dan level. That means it would be actually a master in that Go game. It would not be able to beat the best players, but it would achieve considerable results. Only in 2016, with significant effort from the side of Google, in particular by buying two companies that had the lead, both in Monte Carlo tree simulation and the other in deep learning, would be able to beat Lee Sedol, one of the best players in the world. and that was a real breakthrough. Nobody had hardly anybody, let's say, had expected that it would be possible for a machine to beat a master so early. There were two fundamental reasons. One was a lot of money from the side of Google that were invested in the project. The other side were recent breakthroughs in the area of neural networks, deep learning. We will jump to that also later on when we speak about heuristics. If you are interested in what deep learning actually is, come to one of my courses on media understanding. There we deal with that in detail. It's not so much a problem of strategic playing or strategic planning. It is rather a problem of computer vision that was solved by the AlphaGo machine. Of course, the contest was not fully fair because AlphaGo had invested due to parallel processing decades of training for the game of Go, which is possible in a machine, however, of course, hardly possible for a human being. Okay. So, what makes a game? What are the most important dimensions? Certainly, one of the most important aspects is if it is a zero-sum game, that means if you win, I lose, or if it is a cooperative game where we can gain a higher score if we cooperate and play together. A typical example for a zero-sum game is, of course, chess. You cannot win without making somebody else lose. And a cooperative game is, for example, if you know the game of Carcassonne, where if you decide to cooperate on certain strategies, you can build bigger cities and therefore the end score for all involved players will be higher. So that is the dimension of the reward system. The level of information is also very important, in particular for you in the lab course. There are games that are fully observable. I always know everything that happens on the Go board as well as on the chess board. But the level of information might also be only partial. If you think, for example, of the game of Civilization, you have fog of war, areas that were not explored or not recently visited become blurred, and you don't know whether there are enemy units there, for example, and there might also be an element of chance by using, for example, dice. Okay. That is closely linked to the dimension of whether or not the game is deterministic, which is always the case if it is fully observable, might still be the case if it is partially observable, but need not be the case if there is elements of chance. The move order might be simultaneous, like in real-time strategic games, online games, but it might also be sequential, such as in almost all old-fashioned board games. You will only have to deal with sequential games, sequential move order games. Okay, time structure can either be discrete or real-time. That is closely linked to the move order, meaning that the sequential game will almost certainly be discrete and the simultaneous game will most of the time be real-time. There is the thinkable option that a simultaneous game might still be discrete, but a sequential game can hardly ever be in real-time. Only if you include the playing with the time and the clock in chess, you could argue that it is a real-time game, but that, of course, is not the most important aspect of the game. Feedback type is either combinatorial, that means you have an immediate reward, or real world, where it is delayed. Almost all games that are of interest are real world games. Even tic-tac-toe is a real world game where the consequences of your move do not become immediately most of the time. Okay, here are some examples. Chess is a zero-sum game. It's fully observable. It's deterministic, sequential, apparently discrete, and obviously, what? Combinatorial? No, it isn't. It is a real-world game. I don't know why I wrote that. Civilization, on the other hand, is cooperative, partially observable, non-deterministic, and sequential, and so on. Command and Conquer is a typical real-time game. Okay, so what makes a strategy? A strategy is, in technical terms, not as interesting as it is, for example, in military applications, where it can be quite creative. In the technical context, a strategy is just a sequence of moves. a sequence of moves that you make and that depend on the moves of others. It is eventually always a problem of searching something in a tree. We will show an illustration on the next slide. So the question is, if it is your turn in such a game, how many different options do you have in average? Like in chess, you have between 10 and 20 halfway reasonable options. In Go, you have more, like 40, 50, or maybe even more. And that is referred to as the branching factor. The branching factor determines the complexity of a game to the largest degree. If you have a game with a large branching factor, you need more computational power and or more intelligence of the algorithm in order to solve it to a satisfactory degree. If you have a game with a low branching factor, there is the slight chance that you can kill it by simply using good hardware. So the two fundamental search strategies that you have, and search means to go down the trees of options. You choose one for yourself, you choose one for your opponent, you choose one for yourself again, and so on. One of them is to go down that tree and explore as much of that tree as possible. That is called dumb fast search. One example for that is depth search or the minimax algorithm. We come to that in a minute. It is one of the major educational goals. The other alternative is to act smartly, but that almost ever includes that you have to act slowly. Monte Carlo tree search is one of them. That means you give up the goal of looking at all options and picking the best one, but you invest a bit of intelligence into the question where it might actually be advisable to search in that tree, depending on knowledge or heuristics, on something that you think might be the case, might be valid, and so on. The typical example in this area of algorithms is Monte Carlo tree simulation, the other big educational goal of this course. So that's what you have. You can either try to explore the game fully, that is something that you will try with the low branching factor, or if you have exceeding hardware available, or if the branching factor is high and you don't have that powerful hardware available, you will try to invest as much intelligence as possible. That is what I want you to do in this course. Try to develop intelligent heuristics and translate them into Java programs. Okay, another term that you should be aware of is the so-called search stability. There are two possibilities to fail hard or fail soft. Fail hard means that you try as hard as possible to find the ground truth. That means the best option of all that exists. That is quite deterministic. It is quite stable, it's just another word, but it is also quite expensive. You need a lot of computation power, and in practice you will almost certainly fail, because however low the branching factor is, it's still an exponential curve. So the further down you go, you have a multiplier of 2, 3, 10, 20. You have no chance to get beyond a reasonable size of the search tree, even with the best hardware. To fail soft means to act probabilistic, to believe in heuristics, to try something, to risk something, to ignore maybe interesting areas of the search tree. It is therefore not very stable. You might fail, it might play pointless moves, but it is certainly very much cheaper. So an intelligent, smart search is paradoxically one that is unstable, that can easily fail. Intelligence is frail. Dumbness is rather strong and rather hard, but limited. Just like in life. So if you look at this tree, you see you see the game of tic-tac-toe and the typical tree of strategies. Starting from an arbitrary position on the board, it is your time to move. And you have essentially three options. There are three free slots. And for each of them, you have a look at what your opponent could do. And then you have a look at what you could do. That is one half of strategic planning in the minimax algorithm or in any form of depth search. The other act is, once you have reached the end, to evaluate the outcome. Ooh, that is not a good outcome. Huh? Hey, that is a good outcome. And so on. And then pick the one you like the best. If it is your turn to move, you're always, of course, interested in winning the game. You will pick those that have a 1, where you actually won. However, on the next level, you take the role of your opponent. And there you see, well, he or she will pick the option with the least outcome, because he or she will not want to help you. And then you reverse the point of view on the next level again. And that might go down till the 20th move and so on. In the end, you arrive at the option that shows the best outcome, which is this one. What if you make this move, put the X here, you will always win, which is very desirable, because your opponent cannot both cover that field and the other one in the center at the same time, and therefore you will win. That is the whole idea of depth search, to go in 2 steps. In the first, down as far as possible, cut off if the game is at an end, or at a position where you say, well, this is where my computational power ends, and then go back up. Okay, a numeric example, just to make it even better. On the first level, you pick the best option, meaning the one with the best outcome. On the next level, you switch the perspective, and your opponent will pick something that is best for him or her, and so on the third level. So that is the going down part. At the leaf nodes, as they are called, you do the evaluation, and then you go back up again and propagate the outcome and know what the best strategy for you might be. Of course, if and only if you manage to go through the whole tree in the time given. What does the algorithm for that look like? This one is just from Wikipedia. It is a very simple algorithm. It's of course recursive, because this is always the same action, just from the 2 different point of views. Therefore, this perspective is encoded in the variable maximizing player, which is either true or false. True is the one who is on the move, who would like to who has to do the next move, and false is the opponent. So this assumes a 2-player game, and depth, of course, shows the depth. So how do we do? We start out with a depth of the maximum where we would like to go, like say the next 3 moves or 8 moves, then we will start with 8. And the first clause in the function is, if we have reached a depth of 0, that means if we are at the end, or there is no way to go further, the game is at an end, then return the value that we have. Okay, that's just one clause. The other 2 blocks are the same for both players. The only difference is that the maximizing player tries to find the maximum outcome, and the minimizing player tries to find the minimum. So that's the difference in perspective. What do? You do a recursive call to the same function for the next level, for the opposite perspective, take the outcome, and compare this outcome to the best value that you have so far. Originally initialized with something very, very bad, because we want to have a positive maximal score and not minus infinity. Okay, the other player does exactly the opposite. So you're struggling against each other. You see already from this simple algorithm that strategic planning or strategic game design can be very dumb. This is really a dumb, fast algorithm. It is just going down into the recursion, employing the stack of the programming environment of the operating system in order to store all the variable values and trying to get through until all options are exhausted. If you manage, then you have certainly found the best option, but of course you will never manage in practice not even if the branching factor is just 2, because as I said, then it's still an exponential curve. What can you do to make it better? The one thing that you can do to make it better while not compromising on the quality of the outcome, so to leave it dump fast and with fail hard strategy, as we said before, is to use the so-called alpha-beta pruning. Alpha-beta pruning is a simple idea, but it might be confusing because it involves both perspectives. Consider this search tree with a relatively low branching factor. What we are looking for is a situation where we already know that the maximum that you can reach is this value of 5, is a relatively low value. Why? Because your opponent wouldn't allow anything else. Since we know that, going down in another part of the search tree, we would reach a position where the opponent would have no other option than allowing you a strategy that gives you 8, a higher value, as an output. Your opponent has no better option. The other one would even be worse for your opponent, better for you. Since he or she already managed to push you down to a value of 5 in another option, it is at this exact position that your opponent knows that this whole subtree is something that will never play, will never happen. Since your opponent here just means another perspective in your algorithm, you can tune your algorithm to say that if I reach this point and come to a value here for the minimizing player where we are actually beyond everything that will reasonably happen, so we are in an area, if you like, of wishful thinking, then break it off. The whole subtree is not of interest for us anymore. That is the whole idea. It would also work, of course, the other way around for smaller parts. But you have to keep in mind it's always based on the perspective. The opponent would not allow it. That is the fundamental principle of alpha-beta pruning. Okay. So what does it look like in an algorithm? It's almost the same as the normal minimax algorithm. It's just with 2 more parameters, alpha and beta, for these 2 break-off values. And what you do is you do the same cutoff criterion. You do the same call with the recursion. You give the same parameters, but you pick the maximum of the cutoff and the result for the next subtree. And here comes the intelligence. If you see that depending for the maximizing player, we just played it out for the minimizing player, alpha is bigger than beta. That means we are already in an area of wishful thinking. Then forget this whole subtree, return and play a different strategy and simulate a different strategy, let's say, in order to get out. That is all intelligence there is in the alpha-beta algorithm. It is an improvement over minimax. In the game of chess, it usually eliminates about 14%, I believe, I remember, of all the options. So it's a considerable improvement. However, it's not a dramatic increase in performance. Of course, the first call starts with extreme values so that alpha and beta are at the beginning not in the way for the computation of the optimum. So much for dumb fast, fail hard algorithms. Now let's have a look at smart slow algorithms, in particular at exploitation exploration algorithms, and there at the Monte Carlo tree search, which is the state of the art. First, let's get through with this term of exploration exploitation. What does it mean? We already had it in the dumb fast search, in the depth search, where we said that we want to explore the entire subtree. We didn't do anything in terms of exploitation. We just explored the entire subtree, pick the best option and go for it. As I said, in practice, even with the smallest branching factor, it's simply not possible to do that and get through with it in infinite time. So what you have to do is you have to exploit. What does exploit mean? Exploit means that when you explore your search tree, sooner or later you find options, strategies, ways through the tree that appear to be more promising than others. Exploitation means to look closer in such subtrees and ignore others where the outcomes are average or in average very bad. That is the idea of exploitation. If you include that in your strategic thinking, you end up with a dilemma, because most of the time you don't know when it will pay off to give up a bit of exploration for more exploitation. That is something you cannot know, because you can only know it if you already knew the best strategy, but you're looking for the best strategy, and therefore you're in a dilemma. So how much are you willing to risk to get away from fail hard to fail soft, from dumb search to smart search? That is a dilemma also in real life. Being smart is not always to your advantage. Sometimes it's better to act stupidly but continuously. So it's an image of the real world. The standard solution for this problem comes from the area of bandit-based game. What is a bandit-based game? A bandit machine is a slot machine. Typically, the image is some casino in Las Vegas. There are long lines of slot machines, all of them blinking, and they have usually one arm at the right-hand side, and if you pull that arm, some discs will rotate, and if they show 3 equal signs, classically 3 cherries, you get all the money that is in the machine, all the little dimes and nickels, whatever they play for. That is a typical scene from an American feature film, Hollywood movies. Okay. In bandit machines, it is common that the people who play them, poor folks they are, usually don't play just one machine, but they play a whole sequence of machines and go from one to the next and back and forth again. And the question for those players is, well, the question should be how to get away from their addiction, but within the game, the question is, how can they find the machine that is most likely to produce a big reward, a big outcome for them? Because usually these players believe that some machines are more likely to create a positive output than others. As reasonable beings in a computer science course at the university, you know that this is of course just nonsense. These machines are made only for one purpose, for taking over time all the money from these people. However, that's how the players see it. So the problem is to choose between n bandit machines based on experience. It had shown 2 cherries in the last 5 games each. Ooh, there's a high likelihood that 3 cherries will come along. Statistically nonsense, however, that's how human beings think. And the solution that was developed for that scenario is called the upper confidence bound. It is a function that looks essentially like that. And what does it mean? The upper confidence bound gives exploration and exploitation a weight. That means you explore an area if and only if the UCB exceeds the reward so far. What's the idea? When you play a machine for the first time, this is the number of times you played a certain machine, this is the outcome of the UCB. When you play it for the first time, normally you would have a low will to actually explore it because it hasn't produced any reward so far. If you add this term, it becomes a little bit more attractive. Now you add a value of 3, whatever 3 means, added with some weight. It's, by the way, it's this formula, but it could also be approximated by an exponential function like e by the power of minus nj, for example. But that's not important. The more often you play a machine, the more often you rely on the actual outcome of the games that you played, because the UCB term goes slowly towards zero, meaning that that bonus, that confidence, additional confidence that you gave through the heuristic in the beginning is fading away, fading to zero. So the whole heuristic is this formula here. Each node, each action that you could take in whatever situation you have, in the situation where you pick a move, or in the situation where you are already further down in the search tree, your opponent played something, you answered something, and there you are somewhere in some hypothetical state, and you have to choose the right options of all the options that you have. Then you go with the maximum of the heuristic, which is the reward of that position so far. The position is usually called a node, because this is apparently a graph, and in the graph you have edges and nodes, and the heuristic of how many times you have already played that move. If you haven't played the move at all, you get a high additional value for this term. That means, for the exploration term, that means you give a bit of a bonus in confidence, but that will go to zero if rewards do not materialize. And in that case, of course, such a node will not be visited anymore. That is today considered the optimal solution of the exploration-exploitation dilemma. It is essentially a combination of rewards and a bit of trust for beginners. Okay. It is the centerpiece of the Monte Carlo tree search algorithm, which goes through 4 stages. If you are at a certain position in a search tree, like for example this here, then you have to pick an action. The question is, which do you pick, or how do you get to that position? In every single move, you have to compute the UCB heuristics for the various options that you have, and then you pick the one with the maximum value, which is, as I said before, not just the reward so far, but also a bit of trust in those options that haven't been tried. In a way, you give young people a chance to show what they are capable of. Okay, once you have picked one, you develop a new idea. Sometimes you pick the new idea randomly, or you even simulate it, or you use some other heuristics, such as in the AlphaGo program from Google, they would already use a deep network to pick the best, next best possible options. Then you have to play it out somehow. That was weird in the original Monte Carlo tree simulation. That's why it's called Monte Carlo, because originally it would be played out completely randomly. That was, of course, strange. And then you would take the result and propagate it back in the tree, such as exactly like in the depth search. There's no difference in that aspect. So where was the intelligence in the original algorithm? The intelligence was in the picking of a node, picking of a next move, even though even the next move was sometimes random. Then of course it's not intelligent. Today this method has been enhanced, in particular in AlphaGo, by doing a most intelligent pick based on tons of experience from a deep neural network, and simulation has also been replaced by another deep neural network that would give the most likely outcome for the situation given here. That is Monte Carlo tree simulation. What does the algorithm look like? Let's have a look at the graph first. It shows you exactly what exploration exploitation can do. It is not a uniform exploration of the search graph. Some areas are hardly covered. Some are only covered to a certain extent. And some that look very promising are covered in greater depth. For the breadth of the algorithm, the UCB1 heuristic is responsible. For the depth, the reward so far is responsible, because it will then exceed the UCB1, and therefore you will look in that area again and again and again. And if the gamble turns out to be correct, and this is where the best move lies, you have a way higher chance of finding it than with the normal dumb-fast depth search. However, it is unstable, because after all, this is only about 10% of the entire graph. So your gamble is that it must be somewhere here, because you had first promising results. If it isn't, you have failed. So it's a fail-soft strategy. What does the algorithm look like? It consists essentially of three steps. The tree policy is where the intelligence lies, I said. That is picking the next node where you actually will look for a best option, and then picking the next subnode, then playing it out, and eventually propagating the outcome back to the top node. In detail, the algorithm looks like this. This is what we just had on the other page. The tree policy is where the intelligence lies. As you can see, we compute here in this function best child a value for the best option that should be picked. And what is the best child? Is this function here. This is exactly the UCB1 formula, and this is the reward so far. TU stores the reward, N is the number of visits, so it's an average reward, and C is a weight between the two. So the function best child contains exactly the information that we had to solve the exploration exploitation dilemma. It is then propagated up to the tree policy. Expand also belongs here. That is just picking the next action, which can be done randomly, but also based on some more intelligent heuristic strategy. Okay. Playing it out might be random, or might also be based on more intelligence, such as a deep network. Going back up means to start at the leaf node, going to the top node, to the root node, and changing the outcome values by the score that was achieved and the number of visits increasing by 1. So it's a very simple algorithm that has the additional advantage that it is not recursive and therefore can simply be looped over a time limit, and once it's reached, you simply return the best child you found so far. As I said, fail soft, but smart and slow. Okay, very briefly on the Dijkstra. It doesn't have anything to do with strategic thinking. Originally in 2014 I included it because I thought it might be interested in games where you have to actually move from A to B. Well, that is not really a strategic problem, but very briefly let's have a look into it. Generally, the Dijkstra is for starting at one position, wanting to go to another position, and trying to find the shortest path from there to there. It is a very old algorithm. I already learned it when I was a student. So, and even then it was already old. It only has 2 optimizations. It means to go from all start positions to the end position and looping over all the post-next paths. You always go from one node to the next, so you never define a whole strategy. And the only 2 optimizations is that the next node that you pick is the one where you hope that it is closest to the goal. This hope is constructed by taking the cost of the path so far, so how long did it take you to get from the start to your actual position, plus some estimate of how long it could still take. That is what we would call the simulation in the Monte Carlo tree search. So that is one optimization. Okay, once you have picked something, you actually go there, and then comes the second optimization. Should it turn out that that path to that node is actually lower than what you had so far, then forget what we did so far and go for the new option and throw it away. So along the path, you might find out that you could have reached your current position through a different path that was shorter, and then you switch the old solution for the new one. That means you should arrive, not necessarily, but very likely, at a very short path, at the shortest possible part from the start to the goal. Okay, so much for the Dijkstra. It is a rather simple algorithm. Okay, in summary, when it comes to strategic gaming, the essential problem is the branching factor. Even if it is just 2, we have an exponential function of all the strategies that are thinkable. So the solution requires you to invest a bit more of just alpha-beta search, because you wouldn't get through, even with modern hardware, for a simple game with a full computation of the game. Today's approach is Monte Carlo tree simulation using the UCB1 heuristic for a balancing between exploration and exploitation. Okay, so much for the algorithms. Now for the heuristics. Essentially, there are a few options. You can use databases. In some scenarios with partial information, you can also cheat. Cheating, however, in a different sense than plagiarism, of course. You can improve or change the values for the exploration-exploitation balance and try to improve that. And of course, you can use other methods to limit the branching factor, and you can improve the simulation as well. Okay, so what about cheating and surprise? A strong artificial intelligence will, of course, not be able to be cheated, or doesn't need that to be to cheat. A weaker one, of course, which means a smart, slow one, might actually use it as another form of gambling. You have cheating in many games, like, for example, in strategic games such as Civilization on the upper levels. Your algorithm might actually use information from the game model that would not be available to you in the other way around. So the rules are silently broken by the artificial intelligence. With full information, that is impossible, so that depends on partial information. So mostly for digital computer games, it might make the game more attractive, because the AI might be, the agent might be more intelligent or might appear more intelligent. Human beings have a strong ability to see patterns where there are none. Therefore, it might be possible to make the game more interesting. However, this is very dangerous, because if the behavior of the agent becomes highly unlikely, it might easily turn interestingness into frustration. Therefore, if you use cheating in a partial information algorithm, and it's anyway forbidden here in this course, but it is an established strategy in some games, it involves a lot of user-based testing in order to find the right balance with making the game more interesting, making the computer agent stronger, the strategic planning algorithm stronger, without creating that scenario of helplessness in the user and frustration. Okay, so it involves a lot of intuition and practically a lot of testing by users. Okay, more valid strategies are opening and closing books. In the old days, that would mean to do long simulations of games, let the computer play against each other, let one agent play on the computer against another agent. Some databases are also available, like, for example, in chess, assembled from games of grandmasters. Others are, as I said, generated. They can be extremely big. So the biggest problem in the classic time of programming, of opening books and closing books as well, would be to compress the data. The whole strategy in an opening book is, which is of course always just for the first moves, is to try to drop out of the book as late as possible, in order to save as much of the time that is available for the rest of the game, for the computation and depth search for later stages. That is referred to as dropout expansion. The opening book with Monte Carlo tree search only plays a very limited role. In the old days, it might take years to compute such an opening book, and these years would then be a boost for the quality of the algorithm. It is in a way unfair because years in computers can be parallelized to multiple machines and then be only a question of days or month maybe, like it was in Deep Blue. Whereas a human being can only learn one strategy at a time, one after the other. But what is still important are the endgame databases for the closing of the game. That means if only few options are available, because there is only little material in the case of chess, or most fields are actually full, as in the game of Go, then you can also try to start to categorize the different scenarios that might occur in chess, for example, end games where both players have a rook, for example, and maybe one of them has one pawn more than the other. And these categories can then be filled into a database in order to find the best next move. So where the idea is again to get as far as possible, and when time is running out, to switch to the endgame database. Opening database not so important, I said. Endgame database is very important. In the event what AlphaGo implemented for the selection and the playout of the moves is nothing else than such an endgame database. Yeah, that's why I consider it an exception, because normally you use it on few pieces, but they simply cataloged almost the entire game of Go. And that's why this machine worked so well. There are, the theory says, 3 types of such databases. One that gives you actually the outcome for a given situation on the board. The other one that just tells you how long it will take to actually win that game. And the third one just tells you the distance to the conversion of another known situation. So it's an intermediate between the current situation and one that can be estimated in a better way. Again, it's a matter of data management, because these data can become quite big. There you need an index function, which will usually be a hashing function in order to find it quickly. But all these aspects have been mostly relevant in the old days before big data exploitation. Today we have strong databases, and you are allowed to use database systems in your lab project as well that actually take away that complexity from you. Okay, of course you need an evaluation function. That can be, for example, a tree search. Okay, so endgame databases are actually where the strength of computer algorithm lies. It was interesting for me to see that players would induce into AlphaGo an ability to do creative planning, to actually find strategies that express some artful aspects. That is, of course, not the case. They just explored the entire space of possibilities and put that into a deep network and would rationally pick always the best option. There was no aesthetic component in AlphaGo as far as I know. However, as I said, human beings are pattern recognition machines, so we see aesthetics where they are not intended, as in this case. Okay, dealing with uncertainty is a new thing from the winter term 2020 on. So far, we would always play, until then, we would always play only games with full information. In particular, in the early years, we would play Go, and since then we would play Mancala games because they are almost tailor-made with their branching factor and complexity and rule sets for a lab course such as this. From 2020 on, we will also deal with uncertainty. You have 2 options. You can still go for Mancala, or you can go for the game of Risk, which involves both limited information and elements of chance. And the question is then, how do you deal with that? most fundamental strategy that you do is you guess what you don't know. That is called determinization. Determinization means that you define all the parameters that you might have in your game that are unknown. For example, that you don't know the state of the game because part of the board is hidden, as in many digital games, Civilization I mentioned before. Of course, you don't know the plans, but that is always the case for your opponent. So that is not something particularly new or interesting, but knowing only part of the state is a fundamental difference to a game of full information. Yeah? Sometimes you might even have contradicting information, such as if you play the game of diplomacy, both as a board game or as a digital game, or as an online game, of course. And in many games, and this is probably the most relevant category of uncertainty, there are simply elements of chance. It might happen to you in Civilization that you invest one army after the other and a completely outdated hoplite unit of your opponent beats them all. That might just happen. That might be a result of cheating by the AI, but it might also be pure chance. Okay, weather is another chance aspect. If you play military strategy game, the change of the weather will influence your strategy, but you don't know it beforehand. Okay. However, it has to be admitted that this is not fundamentally different to reinforcement learning in general. Yeah? Reinforcement learning always means that the reward is delayed. What does it mean the reward is delayed? You don't know the outcome before it actually happens, but you have to move long before the outcome is actually produced. So uncertainty does not introduce a fundamentally new category into the problem of strategic planning and strategic gaming. Yeah? Determinization is therefore yet another heuristic approach. What you do there is, in the simplest case, you pick all the parameters that you don't know, for example, the outcome in a battle, and just expect something. Pick a random number. More intelligently, you might sample the results of past outcomes, so-called Gibbs sampling, based on a Monte Carlo, a Markov process, and take the mean and maybe even use the standard deviation, so statistical moments, in order to improve the values that you use for the determinization. In the event Monte Carlo tree simulation, in the simulation part, with the original intention of playing out the game randomly, was an extreme act of determinization, by just picking random numbers. You can go even further, and in every single situation, do a whole simulation based on, for example, a deep network, or a game in a game, and therefore try to find a good guess for what you don't know. And that concept is called determinization. There's a lot of literature on it. It's a big topic in agent-based system, very mathematical, but in the practical application, it comes down to intelligent guessing through sampling, simulation, or whatsoever. So it is actually a reinforcement learning problem inside the game, inside a bigger reinforcement learning problem. Okay, another thing that you can do is you can try to improve your guesses by changing the sampling, but also, for example, by introducing a filtering technique that tries to sort out outliers, such as the Kalman filter, and by reweighting of past determinations, so to improve them step by step. Okay, my recommendation, if you go for the risk scenario and have to deal with uncertainty, is start with simple heuristics. If you have two armies, probably the stronger one will win. And only if those fail, try to implement an algorithm that does such a sampling or such a learning from the data available. With that, I think you can get as far as possible, because, as I said, it is the same problem inside the bigger problem, and therefore heuristics should be fair enough. Okay, now to the various steps of the Monte Carlo tree simulation. Let's start with the selection of the next node. That is the first step in the four-step process. Selection of a promising area, then picking a next best move, and then playing it out, and in the event propagating back the results. So how can you select? Well, the default is, of course, depth search. You implore all possibilities before you go one level further. Yeah, okay. Well, that is suboptimal because the branching factor will kill real time. So you have to tune exploration versus exploitation. And that means, of course, changing the UCB1. Well, I told you the UCB1 is considered, that curve that looks like this, is considered, well, not like this in the end, but until here it's about right, is considered the best option in general today. And it was developed for bandit-based games, which are chance-based. So for a uniform distribution, it should be hard to beat it. However, if you play the game of Go or chess, or in your case Mancala or even Risk, there is no uniform distribution of possibilities. So it should be possible, thinkable at least, to find something that performs better than the UCB1 in such scenarios. So what can you do? You can seed the search with heuristic values and say that if I play chess, I'm usually interested in getting the light pieces out early. No? So the bishops, for example, and so on. That would be a search seeding strategy, and give a higher reward than for moves of these pieces. Then another thing called the first play urgency, that is one of the established heuristics, is that you put down the UCB1 heuristics by a weight that makes it lower, so that moves are exploited earlier, or by giving a higher reward for scores that for nodes that have already been visited in the past. Both strategies work the same. So you can make the C in the algorithm smaller, or you can give the Q function a higher value. The other thing is that you move, that you actually cluster moves. That means that you put all moves of pawns into one category, for example, and say that this category is the one I want to go for. For example, in the chess, the chess endgame, that might prove actually valuable. No? In AlphaGo, of course, the strategy was to more or less categorize the entire game and base the selection on a deep neural network. We come to that in a few minutes. Okay, another thing that you can do and that has proven successful before AlphaGo came along was to use exponential weights. I told you before that this formula with the logarithmus naturalis and stuff is just one option of writing the UCB1. Another one would be to use an exponential function with -f, which also has a characteristic that looks like this. It's just a bit different from the UCB1. In the end, it peters out more strongly than the UCB1 would. And the whole idea of the X3 strategy, which stands for exploration, exploitation, exponential weights, is to replace UCB1 formula with the exponential formula, where A is the set of actions, the size of the set of actions, C is still the weight, the tuning parameter, and X is the average reward, so Q divided by N. All that information is available in the MCTS. So implementing X3 just means changing one term in the next move function. Very, very simple, but has proven very effective because the formula is similar, but still not the same as UCB1. For Go, it has proven, since it is more discriminative, it goes to 0 earlier, to create a more balanced exploration of the search tree, which is to a degree decided. As you remember, the more balanced the search tree is, the more you get closer to a fail hard strategy. Of course, we never go for full dump search because that would lead us nowhere. Okay, yeah, the estimate for a move is again computed by the reward so far plus the benefit we give unvisited nodes based on this function. So it's the same strategy, just a different curve for the bonus that you give. Another thing that has recently gained a bit of popularity is the rediscovery of Thompson sampling. Thompson sampling is an old method from the 1930s, if I'm right. And the whole idea is that you find the right parameter set for a function, the one with the maximum output, where you do a multiplication of what you already know and what you expect to happen. Okay, so what's the huge differences between Monte Carlo tree search and UCB algorithm and this one? There are two differences. First of all, these probabilities are always properly sampled. So it always involves keep sampling, for example, of the probabilities. It's not just an heuristic function, it might be any function based on any knowledge that we have, for example, on games that we played earlier. So this is a generalization, the second term, of what we had, of what we already know. It is not a simple heuristic curve such as in the other cases. It might also look like this, it might be linear, it might be Gaussian, whatsoever, whatever makes sense. And the second important difference is to combine the reward and what we believe by multiplication and not, such as in the UCB, by addition. If we add the two terms, we have a very forgiving formulation for a node. It might either have a reward, or if it's unvisited, it might we might give it a bonus of belief. Not in this case. Multiplication means, geometric organization means that both the reward and our belief have to be high in order to visit the node. So it is highly discriminative, where the exponential weights created a more balanced exploration. Thompson sampling does exactly the opposite. It cuts out certain areas in the search tree that are explored in detail, and the vast majority of the rest is ignored. And that is compensated by using a more intelligent bonus function. Okay? So if you manage to sample the probability function, the second term in the argmax function, well, then Thompson sampling can be very strong. It is typically employed as a helper, as a booster at the beginning of the exploration of the search tree. So it is kind of a form of search seeding or first play urgency. Also, it goes into the same direction by linear combination of the UCB1 and of the Thompson sampling. And that peters out after some rounds of searching in the search tree. That means for the first few simulations in the tree, Thompson sampling will be used more oftenly, so we will be more extreme, and with age, so to speak, we'll give more weight on the more balanced UCB1 in order to make sure that after we explored all that stuff, we also get a bit of information about the rest of the world. So just like in human life. Yeah, there is also a ton of theoretical literature on Thompson sampling. It will necessarily converge to the best possible option over time. Time means infinite time, so practically for us not very relevant. But if we use it as a turbo, as a boost for making the UCB faster, it has proven to be quite effective for games such as Go. Okay. A third option is not to support and benefit certain moves, but to cut away others. In biology, that is called pruning, and since we have a search tree, we can also prune that search tree. How do you do that? Very often you start with so-called unpruning. That means you allow only a few options in the beginning through search seeding, Thompson simulation, whatsoever, and then do an unpruning over time, which would be just like the reintroduction of the UCB1 heuristic. However, this can also be done without any heuristics. You can just say that I always want to move pawns. I never want to move other figures, other pieces on the chessboard. That would also be a form of pruning. Depending on the quality of your strategy, the output will be better or worse. Absolute pruning means that you start off with a rather high belief into the system and have a look at what happens. And after some time you say, okay, these are the 3 best moves so far. I will now only go for these 3 and everything else will be ignored. Yeah. Relative pruning is similar like that, but there it is not an N that you defined, but you go for those who actually didn't produce reward but were mostly visited, and go with these. Okay, so how do you do it if you have with a neural network? How did AlphaGo do it? AlphaGo did 2 things. They computed a network for picking the best option from the search tree, for best position where you could actually look for something else, and for picking the best node there in particular. And secondly, that was the policy network. And secondly, so given a position, they would say this is the best move that you can make now. And they would also say that if you make this move, this will be the outcome. They did that by playing through billions of different positions and of different outcomes of games. That was AlphaGo essentially. And that was done with deep learning, because a Go game can easily be visualized as an image. And if you do that, you can employ all the methods of so-called convolutional neural networks. As I said in the very beginning, if you're interested in that, please come to one of my lectures on media understanding. We deal with that in particular in similarity modeling 1 and 2 in the master program, and in media and brain 1 and 2 as well. Okay, so what they did was a bit unfair. They would train billions of hours of expert knowledge into their networks until eventually they knew the game of Go, and no matter what the situation was, they could more or less say, well, this is how we answered that, and the outcome will be like that. A human being, of course, can never achieve that. That became possible through the developments in the area of artificial neural networks, on the one hand, and on the other side, on the availability of cheap processing hardware in the form of graphic processors. Okay, so that was AlphaGo, but now we have AlphaZero. AlphaGo was originally based on expert games, so they would start to train these networks with the games of grandmasters or of players on different Dan levels, as they say in Go. With AlphaZero, they implemented the same idea from a bootstrap perspective. That means a mostly ignorant algorithm that just knew the rule set would play against itself, would learn what strategies produce positive outcomes, and would thus get itself out of complete ignorance to the same state of basically mastering the game completely. AlphaZero was, interestingly, in the media considered to be a big breakthrough, even though from the insider perspective, it is just obvious. Of course you can do that. Starting with the master games was not the end to AlphaGo. It just meant a starting position, a boost for then letting the algorithm play against itself. To start from zero, without any master information, is just doing the same from an earlier stage on. It's essentially a waste of resources, a pointless waste of resources. However, the media reacted very strongly on it, even though it was just a trick, cheap trick. Okay, well, So much for the networks. You are, of course, allowed to use deep networks, but the computational effort required would be very high. So think wisely whether that makes sense for Kalaha or not. Good. How can you improve the simulation otherwise if you don't have an expert deep network that tells you in a situation what the outcome will be, that is, so to say, able to look into the future and thus reduce the reinforcement learning problem to a sheer number crunching exercise? If you don't want to do that, you can, of course, compute the average reward for any action and then base the simulation on these rewards. That means you don't play randomly, but you, in every situation, you play that move of which you think that it will have the best outcome for the perspective of the player who has to move in that action, in that situation. Of course, that is still heuristic. It's still mostly random guessing what action performs best because it's sampled from past data that comes from different situations. And if you apply something from a different context onto something else, then the risk is very high that you're actually wrong. So another example of fail soft. Yeah, the other thing is the last good reply. So to go not for the original function, but for the first derivative and look at what lies between two moves and pick the action that had the best, or depending on the perspective, worst reply and play that one. Yeah, and eventually, of course, everything is beaten by simply computing the entire game into a network. Good. In the area of backpropagation, you wouldn't believe it, but there are still heuristics there. One of them, the biggest problem of the quality function Q that stores the reward so far is that it is usually not densely sampled because there are so many options. However, you need a dense sampling in order to get a good opinion and a valid opinion of what is going on in that strategic situation. So the one thing that is done most of the time is to treat all moves as being the one that is actually currently picked for investigation. That means here in the scenario of Go, this is not a tic-tac-toe game, but a Go game of 3x3, therefore the moves are different. If you decide on some strategy like putting a piece in a stone into the position of A1, which is up here, then you don't give the reward to the node for the move of A1, but for all other nodes that are involved in the playout, that is B1, A3 and C3. And that means that you create a denser probability distribution for all nodes that are relevant in the simulation of the game. With a denser probability distribution, you have a higher chance of making a good qualitative decision on what a good move was. So that is the simple idea. Not just pick the moves that are actually involved in a certain strategy, but all the others that were involved also in the playout. So to say, a turbo for the sampling. Okay, the Rave heuristic was the state of the art before AlphaGo came along in the game of Go. It is another form of a linear combining what you have so far. UCT is another word for UCB1 plus Monte Carlo tree simulation. So this is the UCB1 heuristic, again employing it with a weight, and for the rest of the time using another heuristic, which is called the all moves as first. We just had it. And then setting that parameter as a sliding one that starts out from a high value. So at the beginning, we give a lot of weight to the all moves as first. And over time, the influence is reduced and the UCB heuristic takes over. That means at the beginning of the game, we do more sampling of the quality function using that heuristic, and over time we give up on that because the density functions for the individual moves are already high, and rather do the conservative strategy of balancing exploration and exploitation. It has proven successful in the algorithm of Mogo, which was, as I said, the first one who reached down level. Okay, so this is another example, like in the Thompson sampling case, of enhancing UCB by not fully replacing it, but by extending it with a second term. And that second term has a strong influence at the beginning and over time goes to zero. So the longer we play, the more we trust in the UCB because it has proven successful in other games. But at the beginning, we give it a boost so that the game starts off more effectively through denser sampling. Okay. A completely different area of optimization is in the real-time strategies environment, where essentially the problems are twofold. The first problem apparently is the management of time. We don't have a turn-based game anymore, but we have simultaneous movement of often large numbers of units of 2 or more players. In the literature, I found that it is assumed that in average, management of time requires you to do like 10 to 50 decisions per second for unit movement, for management of units or cities or growth centers or whatsoever. So that is quite a lot, and it enforces you that you have to act not triggered by a certain point in time, the movement, for example, the last move of your opponent, but by actually game-triggered events, choke points, whatsoever. So this is one area, management of time. However, the bigger problem considered in real-time strategy games is the extremely large branching factor that you can reach. That is simply due to the number of units, the combinatorial complexity of one unit moving in this direction and another one doing this. So you actually have to implement a separate strategy almost for every type of unity or for every specific sub-area of the game plan and so on. There is often a lack of structure, so there is usually not well-defined structure as on a chessboard, for example. Plus, usually you have to do a very complex modeling of your opponents, because you will have fog of war, that is partial information. You are not informed about the movement of your opponent. As a result, we have branching factors that are far beyond what we know from games such as Go or chess or others, and we have to deal with that. And as I said before, the branching factor is in practice the bigger problem than the actual management of time. Okay, however, the fundamental approaches stay the same. Monte Carlo tree simulation and alpha beta depth search are both used in the domain. However, if you look at practical implementations, games that are on the market and actually played by human beings, then it is that the rule-based systems are still dominant. That is also reflected in the game environment for the real-time Empire game that we are offering now from summer term 2022 on. There are demo agents for MCTS and depth search. However, they are not as efficient as the simple rule-based approach is. The task of you as students in this course will be, if you go for Empire, to implement Monte Carlo tree search and depth search in a meaningful way in order to be competitive. Okay, I will on subsequent slides point out what that means in practice. Okay, so the fundamental approaches stay the same. What are the most important optimizations? Apparently, we have to do something with the time structure. There are two possibilities. The one is we can do time slicing. That means, for example, every 20 milliseconds, you look at the best possible option for a unit and decide based on some rule whether you implement it or not. What is the best strategy can then be found out by depth search or Monte Carlo tree simulation. These processes can also run in parallel. A continuous optimization of the game tree, of the strategies tree, and selection of actions out of necessity during the game. The second big option is event-based. So for example, if suddenly an enemy unit appears on the board, you pick the best action that is currently available for your unit, which is in proximity to the opponent's unit. That means again that in the background you can employ Monte Carlo tree search or any other strategy, and in the foreground you keep selecting actions where necessary, so building your strategy on the fly during the game. These are the fundamental options. For the lab course, I suggested you go for time slicing because it's way simpler to implement. All you have to do is to use the clock and every n milliseconds do a decision and take care that you don't exceed the maximum amount of time. Okay, another fundamental problem with the large branching factor is that you have to abstract somehow. You cannot compute or traverse the entire tree of potential actions, but you have to abstract it to a level of methods and tasks where you actually employ the search algorithms. And once you have identified a good fundamental task, for example, like attacking a particular city, you go into the details and define which units in proximity are used for which actions actually. So such a hierarchy can have 2 levels, 3 levels, or even more. It has to be scripted, implemented for the particular game, but it can, on all levels of details, then again use the fundamental search algorithms that we spoke about before, in particular Monte Carlo tree simulation. This strategy, this fundamental approach of abstraction is also considered or also referred to as state capturing. Another fundamental problem is referred to as the level of detail artificial intelligence. That means that you have to implement, if the game provides such facilities, different strategies for battle units, then for example for worker units, for management of production centers, and so on. In the normal case, it does not make sense to mix those, but to keep them separated and only on a very high level, actually either rule-based or again by some search algorithm, combine them and optimize their co-working for the strategic optimization of the goal of the game. But usually battle units will follow their own game tree, their own action plan, and for example growth units will have another. As I said, this is called the level of detail artificial intelligence. Eventually, I would like to emphasize that pathfinding, like for example with the Dijkstra algorithm, is often a relevant problem in real-time strategy gaming because units have to move from large areas. Moves are not predefined as, for example, in chess. So it is necessary to identify the best possible traversal from one location to another, and this is usually done in a divide and conquer form by hierarchical pathfinding, for example, considering those units in a particular region first, and then only if necessary widening it to a different or bigger area in every single of the hierarchies. Again, the optimization algorithm here, the Dijkstra algorithm. Now then, these are the fundamental options that you have, the fundamental problems. What particular heuristics do we have for real-time games? It lies in the nature of these games that they are not as well-defined heuristics as they were, for example, for Go with the Rave heuristics and others, and the particular play-out strategies with deep learning, because the number of games is very big. They are very different types of implementation, sometimes battle-oriented, sometimes production-oriented, or even with cultural aspects and so on. So it cannot be per se said what are the best possible heuristics. However, there are fundamental approaches, and these are the ones that I would like to present to you. Some of them concern only the search tree optimization. I already said that somehow we have to abstract actions. One fundamental thing that is done in real-time gaming is that so-called behavior trees are employed. The idea is that you don't define just an action like move unit from A to B, but you actually define an action by a script, a particular complex, maybe even smart behavior, and represent actions as such in the game tree, which means that if you employ, for example, Monte Carlo tree simulation, you end up with a way more complex evaluation strategy. So the play out takes longer and will be more complex and will be dependent on the game state. But this is, however, a necessity because of the many degrees of freedom that we have in real-time games. Okay, then we already said we need a hierarchy for the actions. Even if they are scripted, they are way too complex in order to use them directly in the game tree. So we build complex actions that are composites of simpler ones, like, for example, attack might be a complex action, which might include movement to the target, and then a particular sequence of attacks of individual units that is optimized in order to have the maximum impact, like in a battle strategy game that would mean, for example, first employ artillery and then do an infantry attack whatsoever. Okay, action hierarchies require a multi-step optimization. That is why we built them. That means that there will be a separate search, for example, depth search for on the high level. Shall we attack? Shall we rather defend? In which area shall we show which behavior? Equivalent actions exist for production side, for example. Once that is decided in the particular scenario, in a divide and conquer strategy, on the low level it can be decided, or it can be scripted if it's a behavior tree, what actions are actually taken in what sequence in order to achieve the goal that was optimized on the higher level. So it's necessarily a hierarchy, even if the behavior is complex and scripted. Okay, these are two concepts that you almost necessarily have to implement also in the simple Empire real-time game that we have in the lab, because otherwise the branching factor would actually kill any form of meaningful implementation of a strategy agent. A third thing that I found in the literature is to automate the finding of the abstractions. This is sometimes done by classification, sometimes by clustering. I found research papers that use the decision trees and k-means. Some also use deep learning, and one particularly prominent method uses Bayesian networks. This is referred to as informed MCTS approach because they implement their hierarchy optimization with MCTS, however, model the behavior of their units in Bayesian networks and combine that in order to arrive at the complex and efficient agent for a particular real-time game. Okay, in the area of simulation, when it comes to the play out, one important concept is to trigger a particular behavior based on certain decision points. These can be hard-coded usually. They are usually not generic. So for example, if a foreign unit appears on the game board out of the fog of war, perform a certain action. And that causes then concrete behavior, or which would be rule-based, or search by Monte Carlo tree simulation, or depth search, or whatsoever, for an optimal response strategy for a given input. Furthermore, there are a few general heuristics that I want to share with you because they are implementable in the lab and obviously reasonable given the particular nature of real-time games. One general idea that I would like to introduce is parametric heuristics. That means that you actually define your actions or action groups, your abstraction that you have, by some set of parameters, and switch the problem, or shift it rather, from search space traversal, so going through the search tree and identifying by exploration and exploitation what might be the best next move, to a problem of optimization of the parameter space. Makes it more abstract, makes the application of particular optimization algorithms possible. However, introduces what we call in machine learning the curse of dimensionality, because these parameter spaces can become very big. These might be vector spaces with thousands of elements and therefore require again then complex optimization strategies that might include again a Monte Carlo tree simulation. However, it is a form of defining the problems of the particular game in a structured way, in a vector form, by defining a set of parameters for the behavior scripts that are used in order to represent the actions. Another thing that is on a very general level of the learning or of the improvement of the agent might be interesting for you is referred to in the literature as computational red teaming. Red team and blue team are two terms from military strategic world that are today also used in IT security when it comes to intrusion detection, for example. The red team is usually referred to as the adversarial, as the attacker, where the blue team is the defender, which is usually you. We are defense oriented. And the idea is that by computational red teaming, that you do a structured improvement process for your algorithm using your properly structured agent, Monte Carlo tree search, depth search, whatsoever, and as the blue team, and let it run against a red team of a rule-based, greedy heuristic that implements strategies tailor-made for the particular game. You can also do that in the present lab course if you go for the Empire game by employing your agent against the simple Empire agent, which is a rule-based agent and works quite well, and therefore serves well as a red team in the scenario of the Empire game. So the advantage of this strategy is that step by step you can improve the quality of your algorithm. In later stages, of course, the red team might also be an earlier version of your agent, and by that you can bootstrap your algorithm to even better performance, as it was done, for example, in AlphaZero for the Go problem. Okay. One particular aspect of that is that you can apply this red teaming aspect on particular part problems that you have, like for example only improving the battle behavior and leaving out the protection aspects that many real-time strategy games have. Another thing that I want to mention is spatial partitioning. That means that since we have a lack of structure in these real-time games, because the game fields are usually very big and the behavior is kind of chaotic, it might always be an option to separate different areas, spatial areas, from each other and do an optimization on the individual areas independently, and from that conclude on the general behavior. That might mean that you separate your game plan into 9 areas, and if you identify in a very early stage that in one particular area nothing much is going on, you spend more of the time that you have for computing your next moves on other areas. That requires then only a heuristic for measuring the amount of action in a particular area, and the second heuristic, of course, for merging part strategies into a whole strategy. A last term that I want to introduce is called a stratified strategy selection. That is a systematic process of first clustering units, situations, whatsoever, by a clustering method or some classifier, like again a decision tree, for example. In the second step, you employ rule-based or learned actions for these clusters, and this might then be combined with the proper depth search and machine learning algorithms in order to optimize the performance for a particular program. So if you reflect that, stratified strategy selection is kind of a summary of the methods that I introduced before. This is in general what you actually should do in order to solve your strategy gaming problem. In summary, databases are still state-of-the-art, in particular endgame databases. AlphaGo invested a lot of money, a lot of electrical current, a lot of emissions into the environment, essentially pointlessly for advertising of something that they hadn't done by themselves, but by some companies that they had bought, in order to show that a machine can beat a human at Go, which is anyway clear after some time, sooner or later, necessarily that would have to happen. And therefore deep networks today are state-of-the-art. The smart slow simulation is today definitely the leading one. Monte Carlo tree simulation mostly outperforms depth search, except for very simple games. Yeah, and if you cannot do otherwise, you can always cheat, but of course in the lab course that is forbidden. That is only for your games that you develop and put, for example, in the Play Store or whatsoever. Okay, the question now is, what can you do? What can you implement in order to develop a cool game? And here are some starting points. I would like to make you familiar with first with the programming environment, and then we go through the different related topics in part 4, and maybe there you can pick up one or the other idea, but you can also go through the scientific literature, of course, which is given in the back matter, and implement ideas from there. Usually the programs of the students are highly creative. Okay, just to remind you, playing a strategic game means that you have to model both the playfield, the board, and the actions, and how you simulate, how you do a move, maybe undo a move, how to evaluate the position. That is the set of functions that you have to implement. Good news is, in our programming environments, both for RISC and for Mancala, that is all done already. So you don't have to care about that, and we don't use the old-fashioned C implementation, which was fast but tedious to improve. We use a Java environment, which is just as well. Okay, there are plenty of platforms for such programming. In the old days, we would use AAA, which is Java-based, has an open API. It is a bit buggy sometimes, but it is a very nice environment. If you like tabletop games, maybe you want to have a look at it. It comprises a lot of games, including Go, and yeah, mostly, as I said, tabletop strategic games. It's developed by an active community. Yeah, we used it for Go until we developed our own environment. MuRTS is a real-time strategy game environment that was developed by the Drexel University in the United States of America. It is very popular among researchers that work on the high branching factors and particular problems of real-time strategy development. We don't use it in the lab course because we have our own environment for this Empire game, but it is, as I said, used in several projects in the academic world. In summary, the most important point is that our lab is based on our own environments for Kalaha, very simple, RISC, bit more complex, and the new Empire real-time strategy game environment. In the TU e-learning environment tool, you find all the resources. There is an activity for that, and there you have the how-to documents. You have the whole programming environment. You have a setup guide, so how to compile your Hello World application. You have for all three games a guide how you implement a game class for a strategy, an agent, a game agent, and in these agents how you do the actual selection of the next node based on Monte Carlo tree simulation. All that is well described. There are even examples for a simple MCTS algorithm, for an alpha beta algorithm, and for a random agent. And you can simply use these in order to improve and implement your own strategies. One thing that is important, and it's also given in the TU Wien forum, is that if you go for Mancala, for games with full information, then you have to implement from 2020 on Monte Carlo tree simulation. Depth search alone is not allowed anymore. It is too boring after all. I want you to implement time into clever heuristics and try to find a better solution for the problem than just dumb fast search. Okay. One requirement that you have to fulfill is that whatever you submit has to be addable to the runtime environment through the user interface. I don't want to have to recompile the entire code and put all the agents together. All three engines have a loading function for new agents, and you have to use that function so that I can do that interactively, because it dramatically reduces the amount of time I need for actually bringing the games together and starting the tournament from weeks to a few hours. Okay, if you have any questions, post them into the forum. All the information is there now. It's free to use. You can use it also for your own project later on. If you do that, of course, please observe the terms in the license statements of the students who develop the libraries and give them full credit for their work. Okay, one last advice. Risk environment is more for the experienced programmers. So if you're a newbie to game programming, maybe you should start off with Mancala. That is more easy to use. They're both reliable and very well developed, but it's more easy to use. Eventually, as I already said, the real-time Empire environment is only for experts or experienced Java programmers in order to develop a first set of search algorithm based on Monte Carlo tree simulation and depth search. Okay, a word on evaluation. Evaluation comes along in two different ways in strategic games. The one is the short-term evaluation in a tournament, and the other one is the long-term evaluation, your development over time as a player. In the individual tournament, usually it's very simple. You play a couple of games, and the quality of the outcome is the number of wins that you actually achieve, or whatever endpoints there is. It's the same in non-strategic games, in sports, and also in strategic gaming. The ranking evaluation over long time is the more interesting one, because the set of players is dynamic. Some players drop out, others come. Rules might change of the game partially, and this is something that is typically implemented as ELO ranking. Apad Elo is depicted here, was a Verban chess player and a famous mathematician, and he developed a ranking algorithm based on the earlier Harkness rank. Mr. Harkness was another enthusiast, that should be as fair as possible. So how does it work? It computes your new score based on your old score that you had, your ELO score. If you're a chess player, you might have 2,000, 2,200 ELO points, or if you're not that strong, you might have 17, 1800s, whatsoever. So you have an old score, and your new score is based on your latest achievement with the real outcome, which is you either won, had a draw, or lost. This is very much chess-based. For other games, it has been, the outcomes have to be weighted between 0 and 1. If maybe there is not even a draw for the game, no problem. You have to define that list. And the estimate what the outcome should be. What is the estimate? given your scores, the score of you and of your opponent, he computes a number that lies somewhere between 0 and 1. 1 meaning that you should actually win if your score is much higher than your opponent's. 0 meaning that your opponent is much better than you are, and therefore you should actually lose. And that formula is then contrasted to the real output. So if you beat the strong player, you will get a big gain. How much gain will you get? That is something that needs to be defined by your league or your functionaries, your officials, and it's usually a question of great concern for the chess players. If you are a very bad player, you're given a lot of chances for improvement with a very high K, and the better you get, the lower K becomes. Of course, if human beings define that, it is always to a degree subjective and will lead to discussions. Approximately, it gives you scores between 1200 and 2800, even though in particular in chess the best players I think are today beyond the 2800. In theory it is open-ended, but of course the differences, even if the best players keep playing against each other, will go towards 0 very soon. Okay, the fundamental rule is the more drastically the real outcome differs from the estimate, the bigger the change. If you beat a strong player and you're not yourself not that strong a player, you have a big boost. And the other way around, of course. That's why good chess players don't like playing against bad ones, because they have much to lose and almost nothing to gain. Okay, in summary, use Java, use a proper IDE. Both environments, Mancala and RISC, include how-to guides of how to set up IntelliJ and Eclipse, the two most used IDEs in that area. Use our environments. This is compulsory. You cannot avoid it. You submit your source code, the build information if necessary, and the binary of the agent class. This must be loadable over the user interface. If it is not, you're simply out of the game. And the README file plus install file that gives all the information on the engine, plus on the installation of the engine. The class name of the project is also well defined. It starts with a prefix of TU for TU Wien, and SGP for strategy game programming, and in the end you have a postfix of AI for artificial intelligence, so that I can put them nicely into my database, which I use, for example, for the plagiarism check. Okay, you have to declare your project name and the project members in the TU registration thread. Please don't forget to do that, it is very important. Okay. So, related topics that might provide some ideas for you of what you can do. Let's have a look into the theory, a bit at least, of reinforcement learning, of deep learning, decision theory, game theory, simulation, and even military strategic thinking. Okay, reinforcement learning is a situation where you have to decide on an action given some input state, but you don't know what the outcome will be, and you will not be told immediately, but only after some time. So this is one of the subdisciplines of machine learning, of classification. Your goal is always to act as well as possible. That means to minimize errors. These errors are called in the terminology a loss. You want to minimize the loss. There are different loss functions, but that would lead us too far. And what you should do is you should learn. If you even make a mistake in early stages, you should try to learn that, and given a similar input state, you should not make the same mistake again. So how do you do that? You do that by providing you a kind of external teacher that gives you rewards. Where do the rewards come from in the Monte Carlo tree search? They come from the playout stage. There you simulate what the output will be, and you see, oh, if I make that move, I will actually lose. Or I will win that game if I make that move. That is a reward, a positive or a negative reward. Generally, since the outcome and the reward is disjunct and temporarily separated from taking the action, you end up exactly in that exploration-exploitation dilemma, or the other way around. And that's why you have to invest all that time in the complex process of the tree search. That is, by the way, of course, independent of the UCB1 heuristic, which is just an optimal solution for some games of solving that dilemma. Okay, necessarily solving reinforcement learning always means sampling. Taking input states, something that you already experienced, somehow summarizing it in one point with the probability density function in one artifact or one semantic category, like an endgame with one pawn each, maybe, in chess, and then sampling the different outcomes for all the games that you already played, so your entire experience. Such a sampling is usually done, as I said, in GIP sampling through a so-called Markov process. If you're interested in that, please look into the literature or come to one of my master level lectures where we speak about them in greater detail and also about Bayesian processes. Monte Carlo means to introduce an element of chance, because however big your experience is, since the branching factor constitutes an exponential factor in the search, experience is always too little. As long as you don't know everything, you can be surprised. So Monte Carlo methods introducing randomness helps you to look into areas which you wouldn't consider normally, and therefore makes your system more resilient. It gives the sampling a wider field of view. It's always advisable to employ that, as it is in the state-of-the-art algorithm of the Monte Carlo tree search. Now, we spoke about deep learning application in AlphaZero and AlphaGo. Why is this good, and where did it come from? The artificial intelligence fields of artificial neural networks is very old. It goes back to the 1950s and 60s, starting off with the McCulloch-Pitts neuron, which was a simplification of natural neurons in the human brain. The perceptron network as a first input processing output, feed-forward, feedback network. For that, the backpropagation algorithm was defined. So it's actually quite old, but it stagnated for most of the time due to a problem that what you learned by loss minimization, so you would compare the outcome of the network with what the desired output would have been, measure the difference, and propagate it back into the network, suffered from a big problem. Backpropagation was not efficient in learning most of the time because it would always just learn the last layers. In the earlier layers, nothing or very little of the loss would arrive. So in the beginning, the net would simply remain ignorant. Only later it would become more sophisticated, but later it was mostly too late. And that was the state of the art in the mid-2000s. When some of the bigwigs of the area of deep networks decided to make some changes. One idea was to train not the entire network from the back to the front, but to pick always just 2 layers and train every single pair of 2 layers on the full loss, such enforcing an adaptation also in the earlier layers, such killing linear gradients, vanishing gradients. Another thing was not to use a natural inspired firing function in the neurons. Now, the McCulloch-Pitts neuron has a firing function. If the incoming potentials exceed a threshold, then the function fires. Well, that is true for some neurons, not for all. It didn't prove successful in artificial networks. Therefore, it was exchanged by a linear function that is more forgiving. It fires a little bit here, a little bit more here, and it fires a bit even more in higher stages. That also improved the training situation. Another important aspect was that with the 2000s and the improvements in computer graphics, very strong graphics processors became available for cheap price, particularly from the NVIDIA company. And therefore it was possible to do big scale number crunching with rather cheap hardware. So for the scientists, it became easier to try new methods. The field became more agile. With these and other improvements like recurrent networks, so-called long short-term memory cells, and many other things, certain computer vision problems were simply solved. In particular, the problem of visual object recognition, finding, for example, a face in an image. It can be done now by a computer with superhuman performance. That means the computer algorithm will make less errors, will have a lower loss than an average human, because a human gets tired and a computer doesn't. And in the event, it can remember more faces. Okay, and the idea of AlphaGo was, and that's the best point in the whole concept, in my opinion, was to consider a Go board a visual image. And then do playout and search by deep learning. Just learn combinations of games, the simulation to the end, and the outcome visually. So if you have that board given in a certain situation, picking the move means the visual comparison through the deep network, and the class label, that is the outcome, is then the move that you should actually pick in that situation. That has proven extremely powerful and improved the quality of the Go algorithm significantly. Furthermore, it was not just used for the picking of the move, but then also for the estimate of what the new situation will actually result in. What will the outcome of the game be? If I make this move, will I win or will I lose in particular? So to look into the future, thus actually destroying the reinforcement learning situation and making the game deterministic without telling anybody, of course. Yeah, and that's why deep learning has proven a massive game changer for the area of strategic planning and strategic gaming. In practice, however, you have to be able to afford the training process. It is very costly and very expensive, also money-wise, costly in terms of computation power, and even mid-range companies for their strategic planning problems, as far as I know, cannot afford doing something like that. And also many problems are not suited to visual evaluation. They don't have a state on the board that could be simply defined. Okay. Below reinforcement learning and the shortcut with deep learning lies the fundamental problem of decision theory. What does that mean? You want to maximize your outcome in a static environment. So you have a situation given, like the board in the Go case, or in the chess case, or in the Mancala case as well, and you want to find out what you can get out for yourself. Utility means your personal gain. There is a lot of theory behind that. It's mostly mathematical. If you're interested, you can look into it and simply type decision tree theory into Google search, and you will see that the usual solution is gaining experience. As we said before, sampling, and sampling. Using Markov processes to find out in what situation, what result can be created, and then employing that knowledge for clever strategic decision making. Yeah, that's actually all there is. The usual implementation is either a hidden Markov model or a normal Markov process. Hidden Markov model has an additional set of variables that deals with uncertainty. If you're interested in that, please come to my Similarity Modeling 1 and 2 lectures, or other machine learning lectures where these topics are discussed in greater detail. The important thing is, decision theory is about maximizing your own gain, minimizing your own loss, maximizing your utility. If you consider not just yourself, but widen your view to all the players involved, which is even in the simple case of the Minimax algorithm, happening, because there you change the perspective with every move. You go further down into the graph. Then you're in the area of game theory. Game theory tries to optimize the utility for all involved players, for all of them, because you cannot expect to the others in the game to play along with your goals. They will have their own goals. So what is realistically possible under these situations, under these conditions, is what is answered by the theories developed in the area of game theory. The most famous strategy there is, of course, the Nash equilibrium. Here it is, Nash solution. That is that the equilibrium will lie between the players, where the expected values are optimal for all of them. Optimal in terms of as much output without hindering anybody else. In computer vision, we would call that a Voronoi tessellation, and it is actually equivalent to the categorical imperative of Kant. The mathematical formulation, of course, depends on how you compute the expected value in your particular domain, which is different in strategic planning in companies, for example, than it is in games. In the simplest case, the expected values might be all the possible outcomes with their probabilities, or in the more complex case of our games with the high branching factors, it is, of course, the result of all the pickings and simulations that we have with vast density functions. So game theory is always about finding an equilibrium between all the players, because we consider them all. Okay, yeah, rarely you will have a dominance of one solution. Most of the time it will be a Nash situation. That is when it becomes interesting, of course. If you have dominance, game theory is basically irrelevant. You just maximize the utility and then for the one aggressive player in the lead. Trembling hand is something that is called that even though you actually would go for the best equilibrium, you cannot, it doesn't materialize because you simply don't have the guts to fight it through. That means you have an introduction of a bit of noise, of a randomness, and the function f defines to how influential that noise is and how much it affects you. 99% of all cases, of course, it affects you negatively. Okay, the maximin solution is one term that you might want to remember or look up, is that you have a lose-lose situation for all involved players, because destructive behavior is a cause of one player causes destructive behavior of the other players, and thus the output is ruined. This is particularly the case in games that are not zero-sum games. So in the before mentioned case of the Carcassonne game, where you build cities and then get scores, if you behave aggressively and are not cooperative, the other players will behave the same, and in the event the score will be lower than it could be for all of you. That is an example for the maximin solution. Okay, another thing that is important in that context is simulation. Simulation is in the Monte Carlo tree search in the playout stage. The entire process of the depth search algorithm is simulation as well. It means to define so-called agents. That is a very important term. Agents are also called actors. These actors have an amount of intelligence. They can perform certain actions. That means, given an input situation, they decide on a strategy and follow that strategy. Agents are independent of each other, however they interact with each other, so they are representatives for the players in the context of strategic gaming, and by watching and computationally simulating their behavior, one can come to a result on the game situation. If I have two actors of the same abilities with the same knowledge in a given scenario of a chessboard, and one of them, let's say black, constantly wins, then the outcome of the simulation is probably that the board is superior for the black player than for the white player. Technically, what you do is you have to implement actor classes for the agents. You have to model the behavior again with Markov processes, improbability distributions. This is basically always the same. And you have to create a form of communication by, for example, playing a move and giving the new set of information to the other player. And you have to do a lot of statistical testing for the checking of validity of your results. Simulations are still to a degree random because the behavior is picked on experience. That might include a strong random component. Furthermore, probability distributions are always incomplete, so suboptimal, and therefore you have to check for the validity of the outcome. Okay, last point where you might look for inspiration for your heuristics by going through the literature in particular and searching online what others did and what others tried is the area of military strategy and tactics. I read a few books in that area of old generals, mostly from First and Second World War. It was to a degree tedious, I have to admit, in order to find out what their strategies actually were. Independent of the ideologies they were following, just on the purely military strategic level. And what appeared to be relevant for me was that they usually make a distinction between the tactical level and the strategic level. Most of the action happens tactically. You hardly ever do anything strategic, and that is quite analogous to what we have in our area as well. Because we said in the beginning, in that tree of possibilities with the branching factor, strategy is just one path from the root node to a leaf node, which is a very weak definition of strategy and far from what we think when as human beings we hear that somebody has a strategy to achieve this and that. We consider it to be actually way more than that. However, in military it is mostly the same. It's most of the time tactical work and not strategic work. So what is tactics? Tactics is, for example, to define the relative lineup. If you're familiar with the game of rugby, for example, then one of the fundamental rules is that the two teams will form two lines that are opposite each other, and the players themselves are responsible to take care that they are opposite a player that is a good match for them. So one of the heavy forwards will always try to block one of the heavy forwards of the opponents, and not one of the fast yet not so strong wingers that form the backward squad of a rugby team. In military it's the same. A strong infantry unit will try to be positioned in front of another strong infantry unit. However, for the gain of that is mostly a defense-oriented strategy or tactics. Another form of tactical behavior is to do reconnaissance, so to remove the fog of war and try to find out what your opponent is, what they are heading for, how strong they are, what kind of armor they have, and many other things more. So reconnaissance is also something that is, with partial information, maybe translatable into an algorithm. Maybe this can be put into some form of Markov process in order to improve quickly certain parts of the data set used for a strategic decision making. One could think of options here. Terrain is also an aspect that is probably in our case not so interesting, because in Mancala the terrain is uniform for all. It's just a group of bins, and beans are moved from one bin to the next. On the strategic, on the macro level, what they do is usually to define a main direction of movement. So they want to target one particular point, and they want to reach that point at this and that date. And maybe they even say they want to use this and that unit. But that often remains very vague by saying that it is just the second army that will hit this and that city in that week. So strategies are very loose and are mostly, I found, defined for for not forgetting what the aim of the whole action actually is, so that people can be reminded. So it's rather a form of validity checking than of actual concrete decision making. Building and forming fronts and armies is, of course, also a strategic action. So I said second army. What does second army mean? It includes this and that unit with this and that artillery support and whatsoever. So maybe this can also to a degree be transformed to the simpler setting of Mancala, and certainly to the setting of risk with partial information. In the Mancala case, formation just means how many beans you have in one bin. They certainly also had, and that is something that I found while reading these books, is they have the problem of exploration and exploitation very much. So if you found a breakthrough point, you always tend to exploit it. This, however, can become very dangerous. We might end up in a pocket, in a so-called cauldron, as it was called in the Second World War. And exploration also might mean that you lose a lot of time and opportunity. In military strategy, I found an analogy to the game of chess. It is very much about the moment. You always want to reach superiority. That is the fundamental goal. And superiority in a near perfect situation can only be reached by gaining the upper hand in a few selected points, there with massive concentration of your material, of your pieces, in our case, of the strategic games, while blocking off the opponent in all other areas with relative limited forces. And that is the second thing. So concentration is one thing. And the second thing is to gain the initiative, to be the one who actually defines, to force your opponent into a situation where he or she has to react on your behavior. If you're chess players, you know that it is mostly about gaining the initiative. If two halfway good chess players play against each other, they will not lose by forgetting one piece or making a dramatic strategic error. It's usually the one that can enforce to have the initiative, whereas the others is always at reacting. That is what it is about. I don't know spontaneously how this can be transformed into the game of Mancala, but maybe one could think of ideas by searching what initiative momentum actually means. If it maybe appears somewhere in the gaming literature, what these colleagues have implemented, and try to implement that in the lab course. So that is the idea of the whole block that we are dealing here with. So maybe this can be a starting point for you to develop interesting new heuristics. Outflanking, cutting off is very, very military based. That simply means to break the communication line of the units of your opponent with the center of intelligence, so the headquarters, so to speak. That cannot happen in games with full information, and hardly ever can happen in games with partial information. So this is something for the military reality where I don't see much potential for us. On the defense side, if you are the one who does not have the initiative, then typical strategies that I found were that they would actually always build reserves. The reserves might be as big as the active units themselves. That comes as a surprise, because one thinks of these cruel wars to be total wars, as they called them, in the sense that they would employ all units. But until very close to the end, in both world wars, that was not the case. Even for the losing side, they would have considerable reserves that they could employ only when needed, and they would also keep them in reserve. So maybe that is also something. Maybe it's possible to define part of the risk setup, play field, as reserves and not use them actively. Kind of using an inverse pruning strategy. Alarm units is something where I don't really see anything, because even with partial information that would help us, the term meant simply that part of the line that were not set up with active units had at least some small alarm units that would then allow, in the case of an attack, to get other forces in. I think that is too abstract or too concrete military-wise for us to implement in the abstract environment. So is the line of retreat, which has no relevance in Mancala, and I think only very limited in risk. There are, of course, bottlenecks on the risk play field. So yeah, maybe it might be interesting. Shock units, alarm units, that's essentially the same. And the most important thing, as I said, is the struggle for the initiative, and that is reached by the counteroffense. So if somebody attacks you somewhere, like here, the best defense strategy in chess, as in reality, appears to be to fight back on some other flank and see who has the better nerves. Okay, so these are some terms for from the area of military. Maybe they can give you some inspiration of what heuristics you can actually develop. If not, then not. In summary, strategy game playing and strategic planning is a simulation process. So you always have to gain experience by simulation. That means sampling data into Markov processes. The simulation means that there is a time between deciding on something and learning if it was good or bad. That situation is called reinforcement learning in the area of machine learning and classification. You must never forget, despite you are looking for your personal optimum, for your utility, maximum utility, that is also the case for your opponent or your n opponents. And that makes it a game theoretic endeavor where the most likely output is a Nash equilibrium with an optimal expected value for all players. You might be able to employ these areas in order to find interesting strategies that can be taken from other application domains and put into your strategic game agent, or you might also pick them from the military. I gave you a list of a few terms where you can start searching, but maybe you develop your own ideas from games that you have played or otherwise experiences that you have made. Okay, that brings me to the back matter, a few links. There is an IEEE journal on gaming, which is the SIG, Computational Intelligence in Games. You can look there for literature. They also have a society where they have their own transactions, so maybe there is interesting information and updates on recent breakthroughs and improvements there. The Monte Carlo search tree, the information was taken from this paper. It is one of the most important papers in the area, and they also have an interest group here, MCTS AI. If you're interested in AlphaGo, that was the original paper by Silva et al. In 2016. It's a very nice description, very easy to read, very, very interesting. Okay, last bit is a bit more information. Everything. The video, this video, of course, the how-to documents, the programming environments, question and answer forum can be found in the TU e-learning environment in TU Wien. The link to the course is this one. It's also given at the end of the video and a second time. If you have problems, please ask your questions there, only as a last resort. And if you have a personal matter that you don't want to discuss in the forum, please send me an email. I ask you for a little bit of patience. I am part-time in order to improve or to maximize my personal work-life balance. I'm only 3 days at the university, and therefore it might take a day or two for me to answer. But surely I will answer. Okay, otherwise, observe the deadlines. Don't forget to register your project. Do Monte Carlo tree search in the Mancala case. That is required. And use our Java. Thank you very much for watching this lecture. If you have any questions, please post them in the forum. Thank you.